Okay, let's dive into one of the biggest mysteries in all of physics. It's a story that involves a pretty wild new idea that the empty space all around us, well, it isn't empty at all. In fact, it might have frozen solid, and when it did, it put the brakes on the entire universe. Right now, cosmology has a problem, a really big one. You see, our best map of the universe, the standard model of cosmology, is facing what some are calling a full-blown crisis. It's been amazingly successful, but it's starting to crack under the weight of new, incredibly precise data. And at the center of it all is one single nagging question. And that question, well, it leads us straight into this crisis. It's a genuine mystery where two of our most trusted ways of looking at the universe are telling us two totally different stories. So, what's the big question? It sounds simple. How fast is the universe expanding? For decades, we've been trying to pin down this number, what we call the Hubble constant. The trouble is, we have two gold standard methods to measure it, and they just don't agree. So here's the problem in a nutshell. On one side, we've got measurements from the Planck satellite, looking at the ancient light from the early universe. Based on that data, our standard model predicts that the universe today ought to be expanding at about 67.4. But on the other side, when we actually point our telescopes at the modern local universe, we get a much faster number, 73. It's a direct conflict between what we predict and what we see. Now, here's the really crucial part. This isn't just a measurement error. The teams doing this work are the best in the world. The results are unbelievably precise. So this isn't a mistake. Both of these numbers are right. And that deep, fundamental disagreement is what we call the Hubble tension. It's a huge clue that our understanding of the universe is missing something. So, where could this missing piece be? Well, a brand new theory suggests we've been overlooking the most fundamental thing there is, the vacuum of space itself. And this is where things get really interesting. You know, we usually think of the vacuum as the definition of nothingness, right? But what if it's not? What if it's actually a physical substance with properties that can change over billions of years? What if space itself can act like a real material? This is the core idea behind a new framework called Vacuum Elastodynamics. It says the vacuum isn't just some passive backdrop for the universe. Nope, it's an active player, a kind of elastic medium that fills everything. And just like any other material, it can exist in different phases. So, according to this theory, for most of cosmic history, the vacuum was in this really exotic state. It acted like a perfect, frictionless superfluid. I want you to imagine moving through a liquid with zero resistance, zero drag at all. That's how the universe was expanding for billions of years, just smoothly, without any friction from space itself. But then, something changed. And this brings us to the most important moment in our story, an event we could call the universe's big freeze, where the very fabric of space-time went through a radical transformation. You can think of the history of the vacuum in 3x. For the first 9 billion years or so in Epoch 1, space was that perfect superfluid. Then came Epoch 2, a sudden dramatic phase transition, a jamming event. And ever since, in Epoch 3, we've been living in a universe where the vacuum acts like a viscoelastic solid. That just means it has properties of both a liquid and a solid, and crucially, it creates friction. And the theory is incredibly specific. It pinpoints this massive change to a very precise moment in cosmic history, a redshift of about 0.641. Now, in cosmology, looking at redshift is like looking back in time. This moment happened about 6 billion years ago when the universe was around 2/3 of its current age. So the main idea is this: the vacuum of space itself froze. The best way to picture it is thinking about water turning into ice. It's still made of the same stuff, H2O, but its physical properties, its structure, and how things move through it, that all changes dramatically. This theory suggests that's exactly what happened to the entire cosmos. And look at this. You can actually see that moment right here on this chart. For most of cosmic time, the vacuum's friction was basically flat at zero. That's the superfluid era. Then, right at that critical point, boom, it spikes in this jamming event. After that, it settles into this new, stable state of friction, which is where it is today. So why did this happen? Well, as the universe kept expanding, all the matter and energy inside it spread out, becoming more and more diluted. In this model, particles are basically seen as tiny defects in the vacuum's structure. Once the density of these defects dropped below a certain point, the underlying grid of space was suddenly able to connect and lock into a rigid structure. It's a process known as rigidity percolation, that exact moment when a loose bunch of stuff suddenly jams together into a solid. Okay, so space freezes over. This big freeze had a massive consequence. It flipped a switch and activated a new force in the cosmos, which brings us to our fourth section, how the universe suddenly hit the brakes. The moment the vacuum became solid, it started to resist the expansion of the universe. This new resistance is called the inertial counterload. The best way to think about it is as a kind of cosmic scale friction, or a drag force that began to push back against the stretching of space. For the first time ever, the universe's expansion was no longer frictionless. So the process is pretty straightforward. It happens in 4 steps. First, the universe is just cruising along in its frictionless superfluid state. Then, at that critical moment, the vacuum jams solid. This instantly activates a viscous drag. And the direct result of that drag? The rate of cosmic expansion physically slows down. So you have to wonder, how fast was the universe expanding before this brake got slammed on? Well, the theory calculates a pristine, unbraked speed, a sort of theoretical speed limit for the expansion, and that number comes out to be 74.69 kilometers per second per megaparsec. That was the true speed of the universe back in the frictionless era. Then, the freeze happened, and the inertial counterload kicked in. And get this, the theory is so precise, it even calculates the exact strength of this braking effect. It predicts that pristine speed was slowed down by a factor of about 0.9735. It's a small, but cosmically huge tap on the brakes. So what happens when you apply that braking factor to the original pristine speed? You get a final braked expansion rate of 72.71 kilometers per second per megaparsec. This is the predicted speed of the universe today after the vacuum is frozen and started to apply its drag force. And that number? Well, that number should look very, very familiar. And that's where it all comes together. We can now connect all the dots and see how this one elegant idea, a freezing vacuum, could explain the entire Hubble tension. It was never about 2 speeds, it was about one universe that changed over time. So let's go back to our original problem. The standard model looked at the early universe and predicted a modern speed of about 67.4, but our telescopes directly measured it at 73. This new theory shows exactly why that prediction was off. It didn't know about the big freeze. The universe really was expanding faster back in its frictionless era. But now, we live in the braked era, where the cosmic drag from the solid vacuum has slowed things down to 72.7, which is almost a perfect match for what we actually measure locally. The conflict wasn't in our observations, it was in our assumption that the vacuum never changes. And all this leaves us with one final mind-bending question. This theory seems to solve the Hubble tension beautifully by treating the vacuum like a real, physical material. But if the vacuum can undergo a phase transition like freezing, if it can literally exert a force and slow down the entire cosmos, what else can it do? It completely changes how we think about the most fundamental component of our reality.